Hi everyone, this is an ND Polytope rendering engine. It can render polytopes up to about 65,000 dimensions, which is way more than you actually need. To start, we have the regular polygons. The triangle, the square, the pentagon, and the pentagram. Surprisingly, this is a regular polygon. These intersection points are not vertices. In fact, it has the same vertex structure as the pentagon. This is the hexagon, and this is a circle, which is actually 100 gon, or hectagon. Let's move on to 3D. This is a tetrahedron. It has 4 triangular faces, 3 meeting at the vertex. This is the cube, with 6 square faces, 3 meeting at the vertex. The octahedron, 8 triangular faces, 4 meeting at the vertex. The dodecahedron, 12 pentagonal faces, 3 meeting at the vertex. And the final platonic solid, the icosahedron, with 20 triangular faces, 5 meeting at the vertex. And this is the largest uniform polyhedron, which basically means it has all regular faces with all vertices being identical. Here is a decagon meeting a square meeting a hexagon. It's called the gray rhombicosy dodecahedron. And now let's move on to 4D. Let's make the coloring scheme nicer, not like that. There. This is the simplest polychoron. The pentachoron is the 4D equivalent of the tetrahedron. It has 5 tetrahedral cells, that's the 4D equivalent of a face, with 3 meeting at an edge. Yes, things meet at an edge here. This is the famous hypercube, or the tesseract. It has 8 cubic cells, 3 meeting at an edge. This is the hexadecachoron. It's the 4D equivalent of an octahedron. It has 16 tetrahedral cells, 4 meeting at an edge. This is special. It has no other platonic analog in any other dimension, except maybe the hexagon in 2D. It's called the icosahedrochoron, or hyperdiamond. It has 24 octahedral cells, 3 meeting at an edge. It can also be thought as the equivalent of this, the rhombic dodecahedron. There we go. This is because the icosahedrochoron can be made by placing cubic pyramids at each cell of the tesseract, while the rhombic dodecahedron can be made by placing square pyramids at each face of the cube. This is the hecatonicosachoron. It's the 4D equivalent of the dodecahedron. It has 120 dodecahedral cells, 3 meeting at an edge. This is the hexacosichoron. It has 600 tetrahedral cells, 5 meeting at an edge. It's the 4D equivalent of the icosahedron. And this is the largest uniform polychoron, which is known as the I need to think about it. Great hecatonicosachoron. It basically means that it has all uniform cells and all of its vertices are the same. Yeah, they really just said that twice. Moving on to 5D. This is the simplest 5D shape. This is the hexateron. It has 6 pentachoric terra, that's the 5D equivalent of a face, with 3 meeting at a face. And yes, things to meet at faces here. This is the pentaract, the 5D equivalent of the cube. It has 10 tesseractic terra with 3 meeting at a face. This is a triaconta dipteron. It's the 5D equivalent of the octahedron. It's also known as the 5D cross polytope. It has 32 pentachoric terra, 4 meeting at a face. This is a uniform polyteron called the demicube, the 5 demicube or demipentaract. It's special because it can be formed by alternating the vertices of the pentaract. What that means is basically cutting off half of the vertices. If you do that to a cube, you get a tetrahedron. As you can see, we cut 4 of the cube's vertices. If we do that to a tesseract, we get a hexadecacorn, which remember is the 40 equivalent of an octahedron. And as you can see, we cut off 8 of the tesseract's 16 vertices. And finally, we have the demicube, the demipentaract. Why do we keep saying demicube? Which, as you can see, you probably can't see. It's formed by removing 16 of the pentaract's 32 vertices. And those 3, the demicube is not regular, are the only regular polytopes in 5 or more dimensions. No more. I was going to say no less, but that doesn't make any sense. And as a bonus, these are the parked scenes. They are basically just parks in more dimensions. This one is a path circling a tree. This is a 4D park. It shows a path sphering around a tree, which I've messed up the scene. That is never a good sign. But as you can kind of see, the path is sphering around the tree, which is the thing in the middle. This one is a path circling a row of trees. I could hopefully get this into volume view. There. As you can kind of see, the path, the gray thing in the middle, is circling a row of trees, which are these. It should be obvious, I think. Moving on to 5D, I am absolutely playing beyond music in this. We have a path gloaming that is a 4D sphere around a tree, which is even harder to visualize somehow. This is doing a double rotation on the ground. This one is a path sphering around a row of trees. Let's see if I can. You can kind of see it sphering around. Probably try getting into Nope, that's. You can kind of see it's a kind of sphere or a cube with a row of trees. It's a bit more difficult. See, it's a row of trees. This one is a path circling a plane of trees, which is really cool when you put it into a double rotation. As you can see, it's a plane, or it can be a single tree being circled by a path. Really cool. I have absolutely no idea how compression is going to destroy this. But anyways, that's about it. Have a Merry late Christmas, I guess, because I'm absolutely not posting this on Christmas in time.